Hello, and thank you for joining me. You're here with data science teacher Brandon, and we're going to be discussing how to select the best features. You'll find that as you build models, you can engineer so many features, and those generally do help, but you'll get to the point where you just have too many, or maybe there's already too many in the data set to begin with, and you'll need to decide which of these are the best. And if you don't have enough rows to support, enough columns, enough features, you'll need to also make sure that you're selecting really the best ones, so that you're not overwhelming your model for the number of rows that it has the opportunity to learn from. Okay. So we're going to review two different ways to select the best features in our model, and we'll use Shap kernel explainer and then sklearn's feature importances, and then view the difference between those two. Okay. So we have standard data science libraries, and today what we're going to deal with is a house price. This works well because there are a lot of columns to start with, and there's going to be even more after we one hot and code and do some engineering of features. Okay, so to get started, I'll go through this as quick as possible, just highlighting the EDA. We just quickly go through this. Pre-processing, we did bucketizing, putting a continuous variable into buckets that will create categories, and we'll create more variables when we one hot encode. Dimensionality reduction, reducing the number of categories in a variable, getting rid of some of these kind of ones that did not occur very often, and reducing them into. So I only one hot encode 3 versus 6. Okay, so reducing that right there. Filling the null values, pretty standard there. And then one hot encoding to get our dummy. So we start with, quite a few columns, and we're going to one hot encode these variables right here. And we get, so pd.getDummies to do that. And we get quite a few. So we end up with 170. We're going to one hot encode a few more to represent these kind of abnormal distributions, where it's almost more like an event that happens at 0, and you have this kind of flat distribution. So when 3 approaches 0, it'll get a 1, and then when it's not, it's a 0. Okay, so do a few one hot encodings like that for those weird types of distributions here. And we end up with a few continuous variables and a whole bunch of one hot encoded variables, a lot of them, right? So it's hard to, we have a decent amount of rows, but it still will be hard for any model to learn from that. So let's try and select the best features, I thought. So let's just look at how our model's trained to begin with. So we have extra trees and gradient boosting. And on the extra trees, if you're not aware with this is a version of random forest. I like this a little bit better. A little bit extra randomness. Extremely randomized trees is what it stands for, but it's a good model. Okay. And so a good ensemble method. Okay. So doing extra trees regressor here, and we get an 86. A lot of overfitting going on here. Okay. And then on the gradient boosting regressor, 96 and 89. So two of my favorite ensemble methods here, and getting gradient boosting works the best. So we'll use that one for our to get started today. Okay. So number of features. I wanted to make this more of a challenge, right? So that we could see, if we could select the best 10 features. You probably want to use more than this in practice, but if we could start with 10, get it reduced down to 10, we have a lot of opportunity to start engineering more features as well. Okay. But just make it more of a competition, right? Okay. Looking at our top 20 features, this is the standard feature importances, the top 20 feature importances here. We're going to do arg sort by the negative number of features here, just to get the top 10 most important. Okay, and then doing a train test split with these new features here, train test split like we saw before, standardize, and then from this, choosing the best 10 features from Kernel Explorer. We went from 99 to 90, and then 84 to 89. So the test score is roughly about the same. It changed a little bit, went down a little bit on the gradient boosting, went up quite a bit on the random forest. I think what I've noticed with random forest is that it is possible. It's more, or it's easier to overwhelm random forest with too many features than gradient boosting. And so you see a bigger improvement here in random forest. Okay. And a little bit of a drop, not statistically significant drop, but a little bit of a drop on the score here for gradient boosting. Okay, let's look at the Shap values. So Shap uses importing that and installing that, and Optuna as well to make Shap works. Import both of those. We don't use Optuna directly, but Shap will call Optuna. Okay, so doing the train test split, kind of initializing this here again. So we're starting with gradient boosting. Our original scores here that we got. Just getting Shap, and so we're going to do 5 background sets from this right here. okay? And then as we put the train summary in with our kernel explainer, we're using GB predict to get that. We're referencing the function, notice no parentheses right here to give us the values. And then we're going to go Shap values equals Shap values, okay? Shap init, this allows us to show the graph, just makes it a little bit more, well, makes it visible. And then we're doing Shap.summary plot, Shap values x test, and displaying the values. We can get a sense of where these values are and see so many of these really don't have an impact. So the difference between feature importances is that it says feature importances is how much r squared is this one accounting for, right? And feature important or Shap values, what it does is it asks what is the impact as I change the value. If I change the feature value, let's look at the reduced version. If I change the feature value from high to low, what is the impact on the final result of my model? So you can see here, as overall quality is high, it has an output, and as overall quality is low, not a perfect linear relationship, but it does reduce the output of this model as well. Okay, and so we get a better sense of what the impact is versus how much it helped with the accuracy. But will this give us the best features, right? So that was the goal here. And so it's really a different way to kind of look at that problem. Because we did 5 background sets, we want to use the average of all of those. And so what we're going to do is this is the average Shap value per feature. We're going to save those to an attribute here. And if we look at that right here, you can see most are just non-existent, looking at this in this swarm plot, and a few have a really large impact. So let's again try the 10 that we set up, and you're able to experiment with this, try 10, 15, 20, and see which way is the best way, because this was a competition for 10, right? So this gives us the best 10, but really we're going to want more to that to get the best overall score. Okay, so just this is for experimental purposes, but realistically you're going to want to use more than 10 features. Okay, so picking the 10 best here and the 10 most impactful features, I should say. So it's reversing the list right here. Going to select those values, top Shap features, doing the train test split, and training with extra trees here as well. So a little bit extra trees and gradient boosting as well. So let's look at the overall final scores here. So actually what I wanted to see is what if we put these together? Okay, so they both choose the 10 best. What if we put them together and choose the best of all of these ones? Okay, so you see here, so Shap values didn't choose second floor square feet, or didn't think that that was the 10th or one of the top 10 most impactful features. Importances didn't think fireplaces was the most, well, didn't really help with the accuracy of the predictions. Okay, so let's put those all together. So I concat that in right here with pandas. I'm going to get the normalized difference here, just taking it the value divided by the total amount in this to give us a sense if there is the value based on the total, dividing it by the total of the column, so we can get how much, what percentage did it make, and then minusing those two as kind of a percentage difference. And then we're going to do this value and just filling the value, the blank values with zeros right here. But what I want to do, this is just for specifically plotting, but do a plot here of the comparison. And you can see what's interesting is the Shap value, they both thought the overall quality was the most important. But you can see here Shap tends to think or made more use of all of the features, whereas importances didn't, right? It's made a very small reduced amount. Okay, so Shap values kind of shows not all over the place. Sometimes second floor, you can see it didn't really, this is where it's 0, where it didn't really think it was important. And fireplaces here, importances didn't think it was important. Okay. So here, doing the bar plot, really again highlighting the fact that overall quality was the most important here. 3-car garage, it did think that was a little bit more important than Shap thought it impacted the final output of the model here. But you can see really again, Shap is a lot more favorable to all of the features, kind of more across the board. Okay, so but let's use the index of that, which would be these all 12 features here, chest train, and we get our ridge score an extra trees of 90.4 and 89 right here on gradient boosting. So let's compare those all together, because who remembers all those, right? So what happens here is when we see this, if we looked at all of those features, or all of the features to start, we got 86 on random forest and 89 on gradient boosting. As we went down to feature importances, the 10 best, we got 90 for random forest and 88. So we went down a little bit on gradient boosting, but went up significantly with random forest. Shap 80.9, and then with both 90.4. And then here we can see 90.2 and 89. So the best for both of these was using the Shap to choose the best features. Combining that with the extra ones from feature importances didn't help, but really turned out to be the ones from Shap. But we can see here that although Random Forest started off not as good as we reduced the number of features, Random Forest was better able to make use, the extra trees version of Random Forest was better able to make use of those fewer number of features. Okay, so thank you so much for joining me today. Don't forget to like and subscribe down below, and I will see you for the next machine learning tips video.